Hey guys, how are you all? I hope you all doing well. Today I am going to resume this video lesson from the topic of stereochemical aspect of nucleophilic substitution reaction. Stereochemical aspect of nucleophilic substitution reaction. See, I'm start from ordinary light. Okay, so say for example, if I am taking the organic compound, I have to look into stereochemical aspect. Okay, how? I will tell you. Stereochemical aspect. Okay, look here. See, this is ordinary light. I passing through the nickel prism. Okay, I am passing through the nickel prism. We will get plane polarized light. Okay, so this plane polarized light passed through the solution of organic molecule. If we pass through the solution of organic molecule, the molecule either rotate plane polarized light or not rotate. Okay, so if it rotate plane polarized light, it can be clockwise or it can be anti-clockwise. Okay, so if it clockwise, D isomer or plus isomer. If it anti-clockwise, it is L isomer or minus isomer. Are you clear? So this angle of rotation, okay, measured by the polarimeter. Okay, polarimeter. Clear? Right. See, if it rotate plane polarized light, what is the condition? One molecule need to fulfill? Okay, so there is a ordinary light passing through the nickel prism. Okay, we will get the plane polarized light. The plane polarized light passed through the solution of molecule. The molecule either rotate the plane polarized light or not rotate. If it rotate the plane polarized light, either it can rotate the clockwise or it can rotate the anti-clockwise. Right? This angle of rotation measured by the polarimeter. Okay, right? So what is the condition if it one molecule which has whether it is optically active or not? Okay, look here. I'm taking this is your propanol. Okay, so this is your central carbon atom. So this is CH3, this is OH. Okay, so this is not going to be optically active. I will tell you why. So if I take the propane 2-ol, so this is propane 2-ol, right? So the first condition the molecule has to fulfill is asymmetric carbon. Okay, so asymmetric carbon which should be sp3 hybridized, right? So first the molecule should have the asymmetric carbon. Asymmetric carbon means the carbon which has the four different group, right? The second condition is non-superimposable to mirror image. Okay, this is the second condition. Look here. So this is your central carbon atom sp3, but is it as the four different group? This is different, but these two are same. Okay, so this is optically inactive. Okay, but in case what is superimposable, what is non-superimposable? Clear? I will explain to you. CH3, CHOH, CH3. If I am putting the mirror image here, CH3, CH3 and hydrogen and OH. Okay, you just take the A molecule and put it over the, okay, keep over the B molecule. At the time the CH3, 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 above is hydrogen, below is OH group. So exactly overlap, right? Okay, if it overlap or superimposable, then it is going to be achiral. Okay, but in case of non-superimposable, that is going to be chiral. Okay, I will tell you of another molecule. So one more example which is given here, that is butane 2-ol. Okay, so look here. So this is carbon, above there is a CH3, below there is hydrogen, here OH, here CH3, CH2. If I am drawing the mirror image of this, I am going to get the hydrogen O, then carbon, then CH2, CH3, then CH3, hydrogen. Okay, so you take the A molecule and keep over the B molecule, that is going to be non-superimposable. Okay, so this is going to be your chiral. Clear? So say for example, if I take this butane 2-ol, okay, in this, if I take this carbon is surrounded, this is sp3 hybridized 1, this carbon is surrounded by 4 different groups. So then we can say this is the asymmetric center or asymmetric carbon. So this molecule, if it is D isomer, it is going to be L isomer. Your D isomer, L isomer together, we can say enantiomers. Okay, two molecules are same, the configuration also same. The only difference is the rotation. Which side? Either it's a clockwise direction or it is anti-clockwise direction. Fine, right. Next, so there is a one point which is here, the sign of rotation, optical rotation, not necessarily related to the actual configuration of the molecule. Okay, there is a configuration here, right? This configuration alone will not going to decide your rotation of the molecule. Okay, clear? Next, I explain to you what is racemic mixture. First of all, this racemic mixture is optically inactive. Why? If I am taking the racemic mixture, there is a presence of 50% D isomer, 50% L isomer. Okay, so 50% isomer will rotate the clockwise direction, 50% isomer going to rotate the anti-clockwise direction. So at the end it get cancelled. So this is optically inactive. So there is a question which is given here, identify the chiral and achiral molecule, each of the following pair, compound and wedge and dashed representation according to class 11. Okay, so look this carbon which has the 4 different group, so this is going to be your chiral. So these two are same, so this is not going to be your chiral. In case of this one, so it is connected with OH, hydrogen, CH3, then one more molecule is this one. So this is going to be your chiral, this is not going to be. Why? Because these two are same. But in case of this one, so this is your molecule, hydrogen is there, CH2, CH3 is there, CH3. So this is optically active one and the chiral. So this is not optically active because it has the same hydrogen too. Okay, clear? Then I am going to explain to you what is retention. Okay, there's a preservation of the spatial arrangement of bond to asymmetric center. Okay, look here there is a left hand side hydrogen is there, right hand side is CH2OH is there, then above CH3 is there, below CH2CH3 is there, the same group which is present in this side also. Okay, the same configuration is maintained, right? This we call it as a retention. Okay, so preservation of spatial arrangement of the bond. spatial arrangement of bond. Okay, preservation of spatial arrangement of bond to asymmetric center. Bond to asymmetric center. Am I right? Right. Okay. So next we go for we are going to explain exactly what is inversion, what is retention and racemization with this example. Look here. This is your left hand side, right? This is your left hand side. This is your right hand side. Okay. So all three groups which is present in whatever the side, the same side which is present. So this is preservation of configuration. Preservation of configuration. Okay. So this we call it as a retention. This we call it as a retention. But in case of here, look here, this one. So this one is present in the right hand side, right? Exactly opposite of it. So here we say inversion. Okay. So this is B, this is A. So here there is a 50% of A, 50% of B. So it is going to be your racemization. Okay, racemization. Okay, where it is racemization, sir? We know that, right? SN2, I will explain in the next. Look here, the first molecule is this one. Here the configuration, the 3 isomer present in the left hand side. Here it is present right hand side. Okay, so as I told you already, if it like this, okay, okay, this is your umbrella, this become a like this. Okay, exactly opposite of it, right? Just to get inverted. Okay, if it in case of SN2 reaction, just to get inverted, inversion of configuration. So because the inversion of configuration occur because your nucleophile attack the back side. Okay, the nucleophile attack the back side. That is the reason why your configuration get the inverted. The configuration get inverted. Clear? Right. But in case if I am taking the SN1 reaction, we know that, right? The SN1 reaction, the first step, it is going to be step 1. It is going to be bond breaking, right? So this is your alkyl halide. Okay, so this is reversible reaction as I discussed in the earlier itself. So it give rise to your carbocation, right? Your carbocation. This carbocation is sp2 iodized one. Okay, now your nucleophile will attack both side. Okay, your nucleophile attack both side. So there is a possibility of, if there is a carbocation is here, CH3, CH2, CH3, hydrogen. Okay, so this is in the planar. Okay, this is in the planar. So this is carbocation sp2. If it OH minus, okay, attack on back side as well as front side. Okay, at the time, if it back side means inversion, if it front side means retention. So 50% inversion, 50% retention. That is the reason why there is a formation of racemic mixture. Understand? Okay, fine. So we will go for the next topic, that is very, very important. Okay, second reaction, the chemical property, the second topic one is, that is your beta elimination or elimination reaction. Look here. If I am taking the one alkyl halide, the halide substituted carbon nothing but alpha carbon. Okay, halogen substituted one considers as alpha carbon. Adjacent to alpha carbon, that is beta carbon. Okay, that is beta carbon. So in a dehydrohalogenation, or beta elimination, the halogen removed from the alpha carbon and hydrogen removed from the beta carbon. So at the time there is a formation of your product CH3, CH double bond, CH, CH3. Okay, so beta hydrogen I removed from here, so first product. In case of second product, if I am removing from here, CH3, CH2, CH, double bond CH2, your second product. So according to dehydrohalogenation, in a dehydrohalogenation, your preferable product is alkene, which has the more number of alkyl group. In case of first molecule, the methyl and methyl, 2 alkyl group is present. But in case of the second product, only one alkyl group is present, that is ethyl. Only one alkyl. So your first product is more preferred one compared to the second product. Are you clear? Right. Shall we go for next? Yes. Here we go. Look here. So there is a 2 product formed here. Okay, 2 product formed here. Okay, so there is a 2 product here, 1 alkyl group, here 1 alkyl group, so 2 alkyl group is formed. But in case of here, only 1 alkyl group is formed, so your A product is more preferable one compared to the B. Okay, fine. Now the elimination versus substitution. Okay, elimination versus substitution. Elimination versus substitution. First of all, I will explain to you. See, look here. If I am taking the 1 alkyl halide, okay, in this, if I am putting the KOH, but your solvent is H2, so this is they can say this one as a aqueous KOH. But in case of the second one KOH, I am put it in the alcohol. That's why they are saying cumulatively alcoholic KOH. Okay, so here there is a formation of base. There is a formation of base. But in case here there is a formation of, this is one radical, this is one radical. This acts as a base, so it leads to nucleophilic substitution reaction. Okay, but in case of here, this will not act as a this is not act as a base, but no, this is act as a base, so it abstracts the proton from the beta carbon atom, so it leads to elimination reaction. But in case here, this is not a base, this is act as a nucleophile. If it act as a nucleophile, at the time nucleophilic substitution reaction, if it act as a base, then it is undergo the elimination reaction. Understood? Right. So one more thing I want to explain here, that is, if I am taking the primary halide, okay, so this elimination and substitution decided by some of the things. One is, what are the factors which are going to decide? The first factor is nature of alkyl halide, whether it's a primary, whether it's a secondary. Nature of alkyl halide, okay, nature of alkyl halide. Then strength of the base or nucleophile, strength of the base and nucleophile. The third one is size of base and nucleophile. This is 3 factors which is going to decide whether it is undergo the elimination and substitution. Clear? The first thing first. Next we go for the, if I am taking the primary, if I am taking the primary halide, primary alkyl halide, if I am taking the primary alkyl halide, at the time it undergo the SN2 reaction. It undergo the SN2 reaction because we know that, right, in primary alkyl halide, your nucleophile can attack easily on the back side. easily on backside. That is the reason why your primary alkyl halide undergo the SN2 reaction. Okay, but in case of secondary halide, if I am taking the secondary alkyl halide, okay, it either undergo the elimination reaction or it undergo the SN2 reaction. It is depends upon the strength of the base. Depends upon the strength of base or nucleophile. Okay, so primary alkyl halide, your elimination or substitution depends upon nature of alkyl halide. Okay, so it is undergo the SN2. But in case of secondary halide, it is depends upon the strength of the nucleophile. If your base is strong, it is undergo the elimination reaction. Okay, but if it acts as a strong nucleophile, at the time it undergo the SN2. Okay, then your tertiary alkyl halide also depends upon two factors. Okay, either it undergo the SN1, because in tertiary halide it is going to form your tertiary carbocation that is more stable. There is a more possibility of SN1 reaction. At the same time, one more possibility is there. There is your alkene might have, after the elimination reaction, alkene might have the greater number of alkyl group. Okay, so if it more substituted alkene also possible under tertiary carbocation, if it formed, then SN1 reaction. If it greater number of alkyl group, that is going to be elimination reaction. Are you clear? Okay. Next, we are going to discuss about your alkyl halide react with metal. That is the third kind of reaction in this lesson. Look here. Your alkyl halide, say for example, if I am taking the methyl halide, it is react with metal. There is a formation of organometallic compound. If it any carbon, if it directly partner with magnesium, then we say this is called organometallic bond. So this we call it as a organometallic compound. Okay, here the magnesium is less electronegative compared to the carbon. So the electron movement going to be more over the carbon. Magnesium, it is going to be less electron density. Okay, because the carbon is more electronegative, so the electron density more on the carbon compared to the magnesium. In this case, we have to maintain dry condition. That is the reason why we are using dry ether in this reaction. But in case if water mixture is there, or other proton containing compound is there, okay, H2O or CH3OH or it is NH3, okay, at the time this CH3 abstract the proton, then there is a formation of your alkane. Clear? Right, this thing you need. Right, next we go for the Woods reaction. We know that, right? So in this case Rx is there, okay, it react with Na. So whatever the number of alkyl group you are taking in case of your alkyl halide, okay, double the number of product is going to be formed. This 2Na and this 2 halide, okay, get removed as a 2NaX. There is a formation of your butane. Clear? Right? Fine. Next we go for the why your aryl halide will not undergo the nucleophilic substitution reaction. Why your aryl halide will not undergo the nucleophilic substitution reaction? First thing first. See, look here. There is a lone pair of electron over the halogen. Okay. This undergo the resonance or delocalization. Due to that, there is a partial double bond character of the chlorine. So we are not able to break Okay, we are not able to break double bond easily. We are not able to break double bond easily. This is the first reason. Okay. The second reason is the halogen directly bonded with your sp2 hybridized carbon. Halogen is bonded with sp2 hybridized carbon. In case of alkyl halide, the halide is bonded with sp3 hybridized carbon. Okay, so here the S character is more. S character is more compared to here. Okay, here S character is less. So S character is more in case of haloarenes. Then we know that, right, in case of SN1 reaction there is a formation of carbocation, right? If there is a carbocation over your benzene, that is going to be unstable. That is not stable. Okay, it is not going to be stabilized if it carbocation formed over your aryl group. Okay. The fourth one is, we know that, right, if I take the haloarenes, okay, here itself, so here the Cl is slightly deactivating, still the lone pair of electron come into ring at the time, the electron density increases. Already the electron rich here. Okay, the electron density is more in case of the ring. Again, the nucleophile is electron rich species. So this is also electron rich, this is also electron rich, there is a repulsion. Okay, these are the four reasons why your aryl halide will not undergo the nucleophilic substitution reaction. Clear? Fine. So next, there is a replacement of, but still we do not want to take, okay, see your haloarenes, okay, this haloarenes, we have to make it, okay, we have to make this haloarenes should involve in the nucleophilic substitution reaction. But how? We have to maintain the vigorous condition. Okay, what is that? So we can use the NaOH. So we are living in the 1 atmospheric pressure, but we have to maintain 300 atmospheric pressure. We are living in the 298 Kelvin, but we have to wait the 623 Kelvin. This is the vigorous condition. In this condition, it will undergo reaction. There is a formation of phenol. Okay, so apart from maintaining this vigorous condition, any other way to conduct the reaction? Yes, there is one more way is there. Okay, so that is, look here, we are going to reduce the electron density and weaken the CX bond. We are going to weaken the CX bond and reduce the electron density. By substituting the electron withdrawing group. Okay, so one withdrawing group substituted, this is A, then 2 withdrawing going to be 2 electron withdrawing group substituted, then there is a 3 electron withdrawing group going to substitute. Okay, but in case of this much as vigorous condition is not needed. So for this 300 atmospheric pressure is not need not. Okay, at the time just we have to maintain 443 Kelvin temperature and NaOH, and there is a acidic condition. Okay, then this one again there is a acidic condition. Okay, here NaOH is there, but the temperature again decreased into 368 Kelvin. But in case of this one, just to warm up with water, we will get the product. Okay, so in this case the OH is get replaced by your nucleophile, that is OH minus. Okay, your phenol going to be substituted, phenol going to be formed. So there is a is there, there is a B is there, there is a C is there. In this, your C is more reactive towards the nucleophilic substitution, then B, then A. Clear? Fine. So there is a one more question which is there. Okay, if I solve, we will complete this video. Okay, rest of the things we will discuss in the next video, that is 5th video. Okay, this is the 4th video. We already made 3 video. Okay, go and watch it. Right, can you think why does NO2 group show its effect only on ortho and para position, not at meta position? Right, see, look here, the X is bonded, here there is NO2, here there is NO2, then here there is NO2. So NO2 here ortho position, NO2 here para position, NO2 here meta position. Okay, so it is only effect if it NO2 is there on ortho and para position, then only it leads to nucleophilic substitution reaction. Then only it make easier on the nucleophilic substitution reaction. But in case of meta position, it will not affect. It will not lead to nucleophilic substitution reaction. Why? Okay, this is the question. Right. Look here. The presence of nitro group at ortho and para position withdraw electron density from the benzene ring, thus facilitate the attack of the nucleophile on haloarenes. The carbocation thus formed is stabilized through resonance. The negative charge appeared ortho and para position with respect to halogen substituted is stabilized by NO2 group, while in case of meta nitrobenzene, none of the resonating structure is bear the negative charge on carbon atom bearing the NO2 group. So therefore the presence of nitro group at meta position does not stabilize the negative charge. Okay, so no effect. Okay, so if it nitro group present ortho and para position, if it nitro group present ortho and para position, at the time the negative charge, okay, negative charge formed, okay, in the NO2 substituted carbon, okay, get stabilized. But in case of meta isomer, it is not possible. Okay, look here. So this is your NO2 substituted para position, right? So here there is a formation of negative charge, right? Negative charge where the NO2 bonded carbon. So NO2 bonded carbon, there is a negative charge is there. So this negative charge is stabilized by this NO2. Am I right? But in case if I am taking the meta isomer, okay, this NO2 substituted carbon, NO2, none of the NO2 substituted carbon having the negative charge. None of the NO2 substituted carbon having the negative charge. So this is not going to be stabilized. Okay. But in case of ortho isomer, here is the first structure itself. There is a NO2 substituted carbon which has the negative charge. So NO2 substituted carbon which has the negative charge. So negative charge is stabilized at the time it lead to nucleophilic substitution reaction. But in case of meta isomer, none of the structure, okay, none of the resonance structure, the NO2 substituted carbon is having the negative charge. Clear? I hope you understand well. Okay, so I will meet with another great video. Till the time, bye bye, take care.